Prof L and welcome to Chemistry Matters. And today we are going to be looking at some more equilibrium calculations using the concentration table. So in the previous video we talked about a relatively straightforward use of the concentration table in order to solve an equilibrium problem. Today we're going to do a slightly trickier one, but hopefully it won't hold too many terrors for you. We're going to use this equilibrium, which we have seen now, I think, a few times before, the equilibrium between N₂O₄ and NO₂, and Kc for this is equal to 4.50 at some particular temperature T. Okay, so how then what is the question that we're going to ask? Well, we're going to put 0.500 mole of N₂O₄ into an evacuated container, and it's going to be a 1 litre evacuated container, so again that makes the calculations easier. And then the question is, what's the concentration of this and the concentration of this at equilibrium? Okay, well that seems like I've given you way too little information to be able to solve this problem. All that we know is the starting concentration of N₂O₄. That's it. That's all that we know. We don't know the final concentration of N₂O₄. We don't know the final concentration of N₂O₂. We do know the starting concentration of NO₂. But again, seems like it's going to be difficult. How do we go about doing this? Well, again, we do a good old concentration table. We do the initial, we do the change, we do the equilibrium. Okay, so, and again, as I say with problems of this nature, write down the pieces of information that you have been given. So, we've essentially been given a single piece of information here. That single piece of information being the initial concentration of N₂O₄. We start off with 0.0500 moles of that in 1 litre, so the initial concentration is 0.500. Now, whoopsie, drew that line in the wrong place. So the initial concentration of NO₂, we know is going to be 0. Now we're not told that, but again we can infer that because obviously before the reaction starts we have no NO₂. Right, we seem to be at a bit of an impasse now, don't we? Where do we go from here? Well, in order to answer the question we need to know this slot and we need to know this slot. The value of N₂O₄ concentration at equilibrium, the value of NO₂ concentration at equilibrium. And there seems, given what we know, no way of getting from there to there. No obvious way anyway. But in fact, of course there is, otherwise we wouldn't be bothering doing this. So what do we know? Well, we know we start off with pure N₂O₄. We let the whole system come to equilibrium, so therefore we must form some NO₂. We must do, okay? So therefore, the concentration of N₂O₄ is going to decrease, isn't it? Because this is going to decrease, this is going to increase. But the question then becomes, right, how much, or by how much is this going to decrease? And by how much is this going to increase? Well, we don't know. We don't, or we can't put a numerical value on this at the moment. But what we can do is say it's going to decrease by something. And we're going to call that something minus x. Okay? That's going to decrease by minus x, some amount minus x. So therefore, from the stoichiometry of the reaction, if this decreases by x, this has to increase, it's a 1:2 ratio, that must increase by 2x. Seems reasonable, plus 2x for that, okay? And so therefore, we can now get the equilibrium concentrations of these guys. We can say, right, the equilibrium concentration of this is going to be 0.5 minus x. And the equilibrium concentration of this is going to be 0 plus 2x equals 2x. And we still think, well, okay, well that's great and all, but we don't know what the value of x is, so how can we solve the problem? Okay, fair enough question. So let's, as we should always do, write the expression for Kc. The expression for Kc is going to be NO2 concentration squared over the N₂O₄ concentration, like so. Okay. So now let's see what happens if we put these values into this expression. Remember that other piece of information that we got given right at the start. We haven't used this yet, but this is going to be important. Kc is equal to 4.5. Okay, so Kc equals NO2 squared over N₂O₄, and we're going to say that that then is going to be equal to 2x squared over 0.500 minus x. So let's make some more room now. And let's see if we can't solve this expression that we now have. Okay? So, what do we got? We have got Kc is equal to 2x all squared over 0.500 minus x. Let's multiply out the top line. 2x all squared is equal to 4x squared over 0.500 minus x. And remember, we were told that the value of Kc under these conditions is equal to 4.50. Right. Oh, where do we go from here? Well, you might not be able to see this straight away, but in fact, this is a quadratic equation. 4x squared over 0.5 minus x is equal to 4.5. Okay? So then, let's rearrange that. So therefore, 4x squared is going to be equal to 0.500 minus x multiplied by 4.5. Okay? And with a little bit of rearrangement, we can convert this into a quadratic equation. So what we're going to get is 4x squared is equal to 0.5 times 4.5 is 2.25 minus 4.50x. And so in other words, 4x squared, okay, plus 4.5x minus 2.25 equals 0. And you're thinking, where's the chemistry, for goodness sake? I didn't sign up for this. I didn't sign up to solve quadratic equations in a chemistry class. Well, sometimes you just have to. But the beauty is that you've all got these graphics calculators that can do quadratics, or you can look up a quadratic solver online, okay? And you can find the solution to this quadratic equation. And you will find, obviously, two roots, because it's a quadratic. One of those roots is negative, so straight away we can forget that one. The other root is positive. Why can we forget the negative one? Because that would give us a negative concentration. And that obviously can't happen. So what we're going to do is we're going to take the positive root. Okay. Now, if you think back, remember we said that the concentration of NO2 was equal to 2x at equilibrium, and the concentration of N₂O₄ is equal to 0.5 minus x. We know what x is now. We've solved our quadratic equation for x. And so now, all that we need to do to find the equilibrium concentrations of these guys is to put x into those two expressions, okay? So therefore, let's get rid of all of that. So therefore, the concentration of NO2 is equal to 2x which is 2 times 0.375, which is equal to 0.750 mole per litre. And the concentration of N₂O₄ is equal to 0.5 minus 0.375, and that is equal to 0.125 mole per litre. Whoa. Very good. Very good, very good, very good. Okay, so we've now answered the question. The concentration of NO₂, sorry, different thing entirely, at equilibrium is 0.750 mole per litre. Concentration of N₂O₄, 0.125 mole per litre. And then in the exam you sit back and you think, yes, I've answered this, I'll go on to the next question. No, you won't, because the one thing you're going to do is you're going to check your answer. Okay? You're going to check your answer, and the way that you're going to do that is you are going to substitute these values back into your expression for Kc, because we said that Kc is equal to concentration of NO2 squared over concentration of N₂O₄. Put these two numbers back into this equation and you have to get the answer 4.50 if these numbers are correct. Okay? And hopefully, if I've done my calculations right, when you plug these numbers back into this expression, this number here and this number here, you then get an answer of 4.5, which means you've done everything correctly. Your Kc value is exactly as it should be. And there you go. Okay, so that is a little bit more in-depth example. And it requires solving a quadratic equation. Now, if you don't know how to solve a quadratic equation, there is that dreaded quadratic formula, which you can plug everything into. Personally, I'm not so worried about the arithmetic or anything like that. I'm worried about the chemistry of things. So I probably wouldn't expect you to use the quadratic formula. I probably wouldn't expect to give a quadratic equation for you to solve. But I would expect you to be able to at least fill out the concentration table and get to this expression here in terms of x. I don't care about the solution for x necessarily, but I do care about you getting to this point. That's the important part, okay? So don't get too freaked out about the maths, but understand the concepts that we're using here in filling out the concentration table to solve this problem. Okay, so on that note, I think we will end it there, and we will see you in the next video.